Now, we must discuss an interesting application of moments in three dimensions, and this is Varignon's theorem. Now say there are n forces, where n can reflect any integer, 1, 2, 3, etc., applied at the same point of concurrency A. Now A is the point of termination of our moment arm R, away from our moment center. And this is shown in the figure below. We have F1, F2, F3, and F4 all acting on A. Now if these forces are concurrent, that is, they all have the same point of origination, then we can apply the distributive property of vectors, such that R cross the quantity F1 plus F2 all the way up to Fn, which the quantity in our parentheses would be equal to our resultant, is equal to R cross F1 plus R cross F2 all the way up to R cross Fn. Now, Varignon's theorem states that the moment about a given point O of the resultant of several concurrent forces is going to be equal to the sum of the moments of these various forces about the same point. That is, we can say our moment about O is going to be equal to the sum of I is equal to 1 to n of m sub I, which is equal to the sum from I is equal to 1 to n of R cross Fi. That is, we can calculate the individual moments due to each force and sum them up to get our resultant. Additionally, if our forces are concurrent, we can calculate our resultant and execute one cross product with respect to our moment arm to determine our moment about our point. In example 2, let's consider a position vector, R given as 3.00, 3.00, 3.00, on which two forces act, F1 and F2. These two forces are concurrent. If F1 is given as 0, minus 1.00, and 3.00 newtons, and F2 is given as 2.00, minus 2.00, and 0 newtons, we want to execute an engineering proof of Varignon's theorem. To begin, we will first calculate the moment about point O due to F1, and we'll also calculate the moment of force about point O due to F2, and sum the results of these two moments to obtain the total moment of force about point O. To do such, we're going to say our moment of force about point O due to F1 is equal to R cross F1. And this is going to be the determinant of our 3x3 array, where our first row is I hat, J hat, K hat. Our second row is our position vector, 3.00 meters, 3.00 meters, and 3.00 meters. Our third row is F1, which is given as 0 newtons, minus 1.00 newtons, and 3.00 newtons. Therefore, our moment of force about point O due to F1 is given as 12.00, minus 9.00, and minus 3.00 newton meters. Now, our moment of force about point O due to F2 is equal to R cross F2, and thus we'll solve the following determinant. The only difference with this determinant is our force vector, where our third row is now 2.00 newtons, minus 2.00 newtons, and 0 newtons. When we execute the cross product, we have 6.00, 6.00, and minus 12.00 newton meters. Thus, we can say our total moment of force about point O is equal to our moment of force about point O due to F1 plus our moment of force about point O due to F2. We'd have 18.00, minus 3.00, and minus 15.00 newton meters. To verify Varignon's theorem, we will calculate the resultant of F1 and F2 and use this within our cross product to determine the moment of force about point O. Our resultant R is equal to F1 plus F2, which gives us 2.00, minus 3.00, and 3.00 newtons. Within our cross product, we can now substitute R within our third row, and thus our moment of force about point O due to R is calculated as 18.00, minus 3.00, and minus 15.00 newton meters. And we see this matches our previous formulation.